Hello everyone. I hope you are fine. This is Omar Fathollahi-Fard. I'm a research associate in ETS University in Montreal, Canada. In this um, seminar, I would like to talk about NP-hard optimization problem and how to solve it, about reformulation algorithms, heuristics, models, and how we can manage the complexity. This is a very important part for students, researchers, when they want to formulate a real problem or a real application, especially in the field of industrial engineering, that this field is very applicable, and we need to do simulation optimization. That is why every industrial engineer needs to know about optimization, operation research, and recent advances in this area. Let me share my screen, and I will start my presentation. So, solving NP-hard optimization problems. What is NP-hard? If a problem has some type of constraints which an algorithm for solving it needs a non-polynomial time, we can name this model as NP-hard. Means non-polynomial time hard. And the main challenge for NP-hard optimization problems is the complexity, because the NP-hard optimization problems are so time-consuming when you want to solve them with exact algorithms such as branch and bound, branch and count, and other exact algorithms. Therefore, we need to use heuristic or meta-heuristic algorithms. Heuristic algorithms is generally want to solve a model based on the parameters and variables to find a near optimal solution. But in meta-heuristic algorithms, we have some random process which are inspired by nature or which are inspired by human process. Many meta-heuristic algorithms are known, such as genetic algorithms and colony optimization, and many other algorithms, particle swarm optimization, and but which one is better? We want to talk about this issue, that if we focus on developing an efficient reformulation, is better than developing an efficient heuristic or meta-heuristic algorithm. Why? A reformulation is efficient if it can reduce the complexity, and it can keep the feasibility. It means that we have the same feasible space for the model, but the constraints must be easier, must be must be more simplex than, or much more simpler than your general model. In the case of heuristic or meta-heuristic algorithms, we have a theory called no-free lunch. No-free lunch theory is a well-known theory in optimization. This refers that there is no optimization algorithm which which is efficient for solving all optimization problems. It means that in the case of NP-hard optimization problems, then we cannot solve the model exactly. Because they are very complex, they are very time consuming, and this is very challenging to solve it. Therefore, many papers, many studies focus on the development of heuristic or materialistic algorithms, but these algorithms cannot guarantee for finding the global solution. They only generate the local, near local solutions, which are efficient, which are optimal, but not as optimal as we expect. Therefore, the main advantages an efficient formulation is to find an NP-hard optimization model very fast, while generating a feasible solution, which meets a global solution, because it is not only optimal, but is feasible. Therefore, this is very challenging issue, and I encourage the students, researchers, to, when they want to formulate a problem, they want to simulate their model as an optimization model, they need to know that how we can simulate, how we can model the model exactly to be efficient and to be more easier for solving. It's very important. We must remove redundant variables. We must remove redundant constraints. So this issue is very important. I want to provide an example for knapsack constraints. The constraints for the capacity, as you can see, is a type of knapsack constraint which is a very difficult constraints when we have many variables. In this example, you can see that I have a model which is minimizing, for example, the cost, and this is some equipments which regards to the capacity of the one facility to be assigned. Therefore, we want to reduce. We want to reduce the unnecessary variables. For example, in this case, we have 6 variables which are binary. These variables with regards to objective can be replaced with one constraints which have the same feasibility as space. It means that the following model includes 8 times x3 plus 6 times x6 has with regard to x3 plus x point, which are lower than equal 1, and both variables are binary. This model has the same optimality and feasibility as space with regards to the above model. It means that we reformulate the above model in an efficient way to have the feasibility and optimality, and makes the original model to be easier, to reduce the complexity, which is it's very important in the operation research area that you know how we can reduce the complexity. For example, we know that because of the capacity, we cannot have both x1 and x2 together, or x2 and x3. Therefore, we can reformulate this constraint, this knapsack constraint, to the following constraint, which is very easy. Therefore, in this webinar, we want to focus on how we can reduce the complexity while keeping the feasibility of a model, and which can we can solve it efficiently. But which type of programming models are preferable? We know that for linear programming, which the variables are continuous, the variables are non-zero and continuous, and we know that this linear programming models can be efficiently solved even we have many variables or many constraints which are linear, because in terms of linear programming, the feasible space is convex. We have a convex feasible, and the hetero solution, the hetero points of this feasible can be easily find. For example, in the operation research course, you will certainly learn about simplex method. Simplex method is a very good algorithm for solving linear programming. In the case of integer programming, we face that it is a bit difficult than linear programming. Once again, do not forget that if you can formulate or you can simulate your problem using linear programming, it is not recommended to do integer programming, because in integer programming, we have integer values for variables. And one efficient way when we can solve integer programming is for linear relaxation. It means that we assume that the variables are continuous, then we can solve, and when using a branch and bound method, we provide some cut to as a feasibility cut to find a feasible solution for the integer programming. It goes without saying that the mixed integer programming are very difficult, because it includes both integer and continuous variables, and the mixed integer nonlinear programming was very difficult, as much as you think. Therefore, we need to reformulate these models, mixed integer programming or mixed nonlinear programming, to linear and integer programming ones. We need to decompose them. We need to decompose them to be able to solve them efficiently. In this presentation, I would like to provide an example for a quadratic capacity facility location problem. It is a very well-known optimization problem. You know this problem as a fixed charge, but the main difference with the general fixed charge is to have a quadratic item for in the objective function. Quadratic, it means that the interaction between the distance and transportation cost. When you can want to ship the equipments into different facility locations, therefore you need to transform them to different locations and different centers. This model is non-linear integer programming. The first item is about for facility of location, the allocation costs, and the quadratic cost. With regards to the quadratic cost is to consider both distance matrix and flow matrix together for equipments and facilities. But in constraint set 2, we know that each equipment must be allocated to one facility, and it's the constraint 3 means that only one facility is able to handle the allocation, and one equipment must be assigned to only one facility, no more than. Constraints 4 and 5 are regarded to the capacity constraints, especially constraint 5, which is exactly knapsack constraint is difficult, and the binary and variables are binary. So in this webinar, I want to solve this very simple, primary, and complex amplifier optimization problem. To solve it very intelligently using reformulations, and then there's the composition and branch and call algorithms. I want to use the reformulation linearization technique, RLT. RLT are some inequalities or some techniques to generate to make the model linear. We know that for the third item in the objective function, therefore this model is nonlinear in the objective function. We replace these variables into one, these variables are binary, and we want to define a continuous variable to provide, to replace it. One very simple reformulation technique is this technique. It show based on this new constraints which can be added, which are added to the main model, we can efficiently know that this new continuous variable are linked with the binary variables. I think in any operational research course, you will certainly learn about this very simple linearization technique. But an intelligent one is to consider this technique to or parts of a model. If I back to the this constraint type 2 about allocation, if we multiplied these constraints using an additional variable, we have this new type of constraints, and therefore then we can use using continuous variable instead of this nonlinear term. Similarly, it can be used for knapsack constraints, for example, as given to constraint 3, 4, 5. Constraint 3, 4, 5 can be replaced using these terms, as you can see. These then we use a replaced continuous variable in the model to solve this optimization problem. Therefore, with regards to another technique is to consider a different way for generating the knapsack constraints in another way, and after multiplying, we can replace the continuous variable instead of nonlinear term. The final model in the car one is a linear model, which is a mixed integer linear programming model. It has many constraints. In addition to constraints 2 to 6, we have following constraints. The first one is and 12 to 15 constraints set were introduced using RLT techniques, and or equations can be considered. They are multiplied exactly as defining by the RLT inequalities. RLT inequalities that now we replace them in the main model. So we have a new reformulation for the model using linearization technique, RLT techniques. And now we want to provide different linear relaxations to have a comparison. We can reformulate a new bond if, for example, we selected a type of constraints and 10 and 11 constraint set. 10 and 11 is this type of constraints, which are very important. And different other relaxation model, reformulation relaxation models are created. What is the goal? The goal is to find a relaxation, a linear relaxation model, which is more efficient than the basic model. We know that the basic model is so time consuming when you want to solve a large scale. And in the case of nonlinear, you must use, for example, nonlinear solvers such as Baron solvers. But we want to provide a efficient linear relaxation. So after some analysis about optimality gap and the CPU time for some benchmarks, we can see that each of the reformulation model has some advantages and disadvantages. We want to find a reformulation model which has the lowest optimality gap. If a model has a very large optimality gap, it means it's not suitable. But another important issue is to have a very less CPU time for solving, because what is the goal for reformulation? The goal for reformulation is solving the main model in a fast way, very quickly. So we can see the time consuming for each instance and RP gap. We can see that some reformulations are acceptable. For example, the second one, also 5-1, in order. Since the reformulation, linear reformulation number 2 has the lowest number of constraints. It has only 3 constraint sets in comparison to the general model, to the main model. But it is linear and efficient. Therefore, we selected the second model as an efficient because it has the lowest number of constraints to keep the feasibility and to find an optimal solution. We now want to apply Bender's reformulation. What is Bender's reformulation? Bender's reformulation is a very widely technique for solving mixed integer programming models. When you have both integer and continuous variables in your model, then you can decompose it into two different models, a master problem and a sub problem. Therefore, the sub problem for this, I define the third term in the main objective. The third term I get it from the main model RL2 model, and I get these type of constraints. I now assume that these variables are parameters. It means that I assume that these parameters are solved. Then I want to solve this linear model. The sub-problem is linear. It's a linear programming. The objective function is linear programming, is linear, and the constraints are linear. For linear programming models, we can provide a dual problem. The dual problem has conversely type of constraints and a similar global solution in comparison with the main model. So we now reformulate the primal subproblem to the dual subproblem, and note that both because of linear programming, because both these models are linear programming, therefore the optimal solution is the same. It means that this optimal solution for this model is the same as this model. As I know, you can understand dual problem in your operation research course. We reformulate these constraints into dual variables for the objective function, and conversely with regard to objective function to the constraints. Therefore, then we want to solve this dual subproblem and get this solution to put this solution in the main master problem. And the master problem is this, which the constraint set 33 is the optimality cut. This constraints and this variable for, as you can see, it will be updated per iteration for the Bender's decomposition for algorithm. And when we apply these constraints, it helps you to have an optimal solution which is efficient. The algorithm is ended when we know that the solution from Bender's reformulation is feasible for the main model, or the gap the gap from the solution of the dual problem and the Banner's formulation problem is very low, and we can consider that if, for example, for each per iteration, the Banner's formulation has not changed, that means that we can finish the algorithm. So now we want to focus to solve this Banner's formulation model using this dual subproblem and the Banner's formulation by branch and cut algorithm. And in this number of instances, when we know that what is the optimal solution, we can now compare the process time of this reformulation model which other models. For branch and cut, we have not enough time to focus on this algorithm. In this seminar, I generally want to provide this new insight for you to focus on how to formulate your model and how you can reformulate it in an efficient way to solve it and using the composition reformulation and the composition techniques which are efficient for your optimization problem. And you can see that from in average, our formulation model with using the branch and cut algorithm for the decomposition reformulation, then we can solve this reformulation using branch and cut or branch and bound or other algorithms which are using linear relaxation for solving an optimal solution. So the goal of this seminar is to provide this idea in your mind that what is the goal for solving. I encourage you, instead of developing many algorithms which cannot solve the model intelligently, which they cannot solve the model in an efficient way, you must try to reformulate the main problem to have both feasibility and optimality features. All in all, I would like to thank you for your time and attention, and I will be available for your questions with regards to these topics that I introduced you. Have a nice day, and bye-bye.